Now coming to the last part of this last video, that is, let us say, that is conformation of cyclohexane. Just I was talking to you that by twisting or bending a three strain it develops. Got it? That is your Torselian strain, then angle strain, and we can say that steric strain. Got it? So what I said you, what topic was that cyclohexane is more stable than cyclopentane. Now do you know that cyclohexane, when bending and twisting, it can be represented in different manner? Do you know it? Alright, see here. This is your cyclohexane. This is your cyclohexane. When you bend or twist, it can be represented. See here, 1, 2, 3, 4, 5, 6. If you are bending, it can be represented in this way also. It can be represented. One, 2, 3, 4, and of course this will be bending little bit. Let me bring this one here. Then it will be, you can see the bend, correct. So this is your 5 and this is your 6. Alright, this is your 5 and this is your 6, we can say that. Clear? So this is, what is this one as? It looks like a chair, isn't it? It looks like a chair. I will make it little bit more better, this one. And then it will represent a chair properly, we can say that. So this is represents more like a chair. So 1, 2, 3, 4, 5, 6. See, you can see that. It can be represented in this way. This is called as chair conformation. Alright, now this chair can be represented in this way also. Alright, it can be represented this way also. 1, 2, 3, 4, 5, 6. This is flipping. I'll tell you what is flipping. Now, it can be represented in this way also. Alright, see here. 1, 2, 3, 4, 5, 6. What is this known as? It is known as board conformation. This is said to be as board conformation. These two are the chair conformation, and this is a normal cyclohexane. So you can see that cyclohexane, on bending and twisting, we get different conformers. Different conformers we are getting. These are the conformational isomers. We can say different conformers. Chair conformers, board conformers. We can say that we are getting it. Fine. Now, next is, that is in chair conformation of cyclohexane, we can say all bond angles are 111 degree. All bond angles in chair conformation, the bond angles are 111 degree, which is very close to, that is normal tetrahedral, which is 109.5 degree, which is very close. Alright, due to the, what you can say, this reason we can say that cyclohexane, the conformers which is showing, is more stable in nature than that of cyclopentane, isn't it? What Bayer said, that cyclopentane is the most stable. Alright, because the angle of deviation is the least, so hence it is the most stable. But later on we came to know that it's not the most stable. Cyclohexane is much more stable than cyclopentane. Why? You are seeing the reason here. Because it shows a bond angle of 111 degree, which is close to 109.5 degree. Very, very close. The carbon hydrogen bond angle is 109.5 degree, which is very close to it. Due to which it gets staggered. It shows staggered conformation. This particular one is. Alright? Clear? Now, in this staggered conformation, you can see here, for example, here you can see this, let me draw it, this one, okay, fine. Let me draw it here. So, the line, we can say, this is not a line, it is the bond. This sort of bond you will be getting and this sort of bond we will be getting it. Alright, so one is known as the equatorial bond and another is known as the axial bond. Axial bond is perpendicular to the, what you can say, the carbon atom. It is perpendicular, alright, to that part of the, that is carbon atom. And this, the equatorial bond is along with that of the carbon atom. It's along. So this is your axial and this is your equatorial. Again, this one is your axial, and this one is a equatorial. This is axial, this is equatorial. Again we can say this one is axial and this one is equatorial. This is axial, this is equatorial. In this way you will be getting it. Axial, equatorial, in this way you will be getting it. The axial bond means which is perpendicular. Alright, and equatorial means which is along the plane of that particular carbon atom. Along the plane of the carbon atom. And the one which is perpendicular, that is called as the axial bond. We can say that. The axial plane, we can say that. Clear? Now, what we find is here that here we will see here. See here. This C4, this is a fourth carbon, this is a third carbon. Alright? C4 and C3, that is C of the axial. C4, that is a fourth carbon atom, the third carbon atom. Got it? Of the axial bond. What is this? They are opposite in this way. They are not on the same side. They are in the opposite side. They are known as what? They are nothing but known as a trans isomer. Suppose if I do it in this side, it will be what? It will be known as a cis isomer. If I put it in this side, then it will be a cis isomer. We can say. Now it is a trans isomer. We can say. Got it? So it is coming under the trans isomer. We can say that. Is it clear now? For example, one more I will show it to you. That is, we can say this one, and we can say this one. We can say that. Clear? So these two are the axial. So this is coming under what? Trans isomer. But if I draw this particular side, then it comes under what? That is a cis isomer. Similarly, if I draw it in this way, now this is axial. Now this and this axial. Alright, so they come under what? That is nothing but on the same, they are on the opposite side, diagonal side. It's coming under trans. And this particular one, that is along this, it is coming under the equatorial bond. This is your equatorial bond. We can say that. Again, this is your axial, this is your equatorial. In this way, we can come to know this is your equatorial bond. So, in this way, what we find is that, again I repeat, if it is on the same side, it is a cis, and if it is on the diagonally, then it is known as a trans. We can say that. Clear? In this way, cis and the trans isomer also we can find it out in case of chair ice conformers. We can say that. In case of chair, that's you have to remember it. One, it is perpendicular, it is your axial, and the one which is along the carbon atom, along the plane of the carbon atom, that is known as equatorial. That's it. This much you have to remember it. Now, next is change of this conformers to this particular conformers. You can see I am changing the side. Just I am changing the side. This is bent towards the left. This is bent towards the right. Change from one form to one conformer to another conformer. It is known as what? Flipping. F-L-I-P-P-I-N-G. It is called as flipping. Change from one conformer form to another conformer form. It is called as flipping of the isomers. It is known as. Alright? Acha. Now next is the boat conformers. The boat conformation is less stable than that of the chair conformation. Alright? It is less stable. Why? Because the boat conformer is having 11 kilocalories energy more than that of the chair. What I said to you, the boat conformer is less stable than the chair conformation. Why? Because the boat conformation is having energy 11 kilocalories per mole. Energy is more. So if energy will be more, the stability will be less. I told you earlier, if energy is more, stability is less. So boat conformation is less stable than that of the chair conformation. Got it? For that reason, the boat conformation is less stable. Moreover, in case of boat conformation, you can see the boat conformation. The hydrogen atom, this is the hydrogen atom. This is called as a flagpole hydrogen atom. The name is given as a flagpole because it looks like a flagpole. This one, it's looked like a flagpole. I don't know the scientists they are saying. It's looked like them. So hence it is known as flagpole hydrogen atom, and they are eclipsed. The flagpole hydrogen atom, that's it. They are eclipsed. The hydrogen, which is atom which is there, the flagpole hydrogen atom, they are eclipsed. Eclipsed in the bond angle is 0 degree. We can say that. Due to what you can say, this particular reason, as it is being eclipsed, you know that you already have seen it. The eclipsed in the energy diagram which I have shown you, the eclipsed is less stable in nature than that of the, what you can say, gauge or anti. We have seen it already. So here also same thing. As this hydrogen atom is eclipsed, we can say that for that particular purpose, what you find is that it is less stable in nature because eclipse is having more energy. So stability is less. You have seen the diagram. You can go back to the diagram and you can see it. That eclipse energy is more in the potential energy diagram. It is more. So if the energy is more, the stability is less. So hence here also, as the hydrogen atom, the flagpole hydrogen atom is eclipsed, due to which, what you can say, the stability is less. So what I said you, in case of boat conformation, the boat conformer is less stable than the chair conformer because 11 kilocalories per mole energy is more in case of boat. And second thing is that the flat pole hydrogen atom is eclipsed, due to which what you find is that energy automatically increases. And hence boat conformers is always less stable than the chair conformers, we can say that. Got it? You understood? In general, we can say the conformation with bulkier substituent group. Suppose if a bulky group is attached to a conformation isomer in the equatorial position, we can say that, then it will be a preferred conformation. Why it is preferred? Because that is more stable. What I said? If a conformer is having a bulky group at the equatorial position, then that is a preferred conformer. Why it is the preferred conformer? Because the bulky group present at the equatorial position makes it more stable, the bulky group at the equatorial position, due to which you find that it is more stable in nature. At the equatorial position, the bulky group. Now how it is? Let me draw one and let me show it to you. Then you will come to know the bulky group at the equatorial position. Now let me draw a chair conformer, we can say that. Let us say this is first carbon and the second carbon. Got it? And this one, and that is what you can say, this one we can say we are having it. So this is not exactly in this way, it is in this way little bit, and this is perpendicular, this one is clear, the second carbon atom, this is the first carbon atom. Let me write it. So we are having CH3 and CH3, and we are having H and H. So in the axial position, in the equatorial position we are having the CH3 group, and the axial position we are having the H and H, we can say that. Alright? In the equatorial positions. So you may answer, sir, this one you said it is axial. Fine. The angle was, what I said, it is bent slightly, it is bent. That was perpendicular, in this was straight line I have made it. For that reason, this is a straight line. See, I have made it. If the carbon atom is this, is a straight line. This angle is 90 degree. Here, this angle is 90 degree. You can see this angle is 90 degree. Mind it. Try to know which is perpendicular, which is axial. So this is equatorial. These two are axial. You can see. So in the equatorial position, if the group is a bulky group, CH3 group is a bulky group compared to H atom. So hence it is, as it represents a bulky group, which is more stable in nature. Suppose if I replace this as H and H, and this I make it as CH3. So in the axial it comes CH3, and the equatorial you can come, that is H atom. Then it is less stable in nature. Understood? This is the equatorial position which is having H atom. Previously what I made, in the equatorial position that was the CH3 group, the bulky group was there. So if the bulky group in the equatorial position makes it, what you can say, more stable in nature. We can say that, more stable. There is a preferred conformer, so to say that. Understood? Got it? Any axial position, any equatorial position, the bulky group is there, then it's understood to be as a preferred conformer. Preferred conformance means that particular conformation is considered to be as a stable conformation, we can say that. Clear? Now let us see in case of boat what it happens. In case of boat, what it happens. Now see here, this is a boat conformer. Here also we are having the bulky group. Here also we have the bulky group. Let us say we are having here CH3 whole, that is twice or whole thrice C, we can say that. Here also we are having CH3 whole thrice C, and this one is H and H we are having it. So these two are the equatorial positions, we can say that. These two. Got it? So in the boat conformation, the preferred orientations, the preferred conformation is if there is a bulky group at the first and the fourth position. First and fourth. 1, 2, 3, 4. If the bulky group are present at the first and the fourth position, bulky group, see this is a bulky group, it's present at the first and fourth position, then it is said to be stable. It is considered to be as a preferred conformer. Got it? In this way. So this is about this conformation in alicyclic compound, that is what you can say cyclohexane, one of the example I have given you, where you have seen it, the boat conformation, the chair conformation we can see, and the boat conformation is less stable than the chair conformation, everything we discussed about it. Thank you very much.